Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome everyone for the session on recent advances in parallel algorithms. Traditionally, parallelism has gotten a lot of focus since the 70s and the 80s, and it still continues to be an active area of research. And so in this session, our goal was to actually bring together some of the recent work that's been happening on how we deal with communication, irregularity, and breaking dependencies. And so our first talk today is by Gray Ballard. He is from Sandia National Labs in Livermore, and he recently graduated from University of California, Berkeley, working with James Demel on communication avoiding algorithms, and so he's going to be talking more about that. Gray?
Thanks very much.
So before the talk starts, I forgot to mention that we're going to have a more like a conference-style session. So 3 talks, 25 minutes with 5 minutes of Q&A. So hold on to your questions till the very end. And since this is recorded, even though we can hear you here, we prefer that you actually ask your questions when there's a mic runner with you, so that the questions are recorded properly. I'll remind you again at the end of each talk. Thank you.
Okay, thanks, Lana. Thanks very much for the invitation to talk. So I'll be focusing on parallel algorithms for dense linear algebra, and I'll talk about what I mean by avoiding communication. So high-level summary of what I'll tell you. First, communication is expensive, and I think you probably are all convinced of that, but not just expensive in terms of time, but also energy. And I'll tell you what I mean by avoiding communication. So for algorithms like dense linear algebra and sparse linear algebra and related computations, we can actually prove lower bounds and tell you how much communication you have to do if you want to solve these problems on a parallel machine. And this theoretical analysis, these lower bounds that we get in theory, they help identify where the state of the art is not yet optimal. So identify a gap between the best algorithm and the best known lower bound. When those gaps exist, then we can start to work and see if either the lower bound could be improved, or better yet, we'll get a new and better algorithm. And I'll show you some examples that when we do get these new, better algorithms in theory, we can translate it to tuned code that speed ups in practice. And when we come up with these new algorithms, often we have to be careful. So sometimes they require careful, tuned implementation for particular architectures to get performance. Often there are trade-offs that you need to be able to navigate. Sometimes you trade off reduced communication for more computation, for example. And then also, these are numerical algorithms, and you have to be very careful about the numerical properties of the algorithm. So sometimes changing the algorithm makes it run faster, but you have to make sure that you're still getting the correct answer, or the accuracy that the computation deserves. Okay, so that's a high-level summary, and I thought I'd start with one of the most fundamental computations for linear algebra, and that's dense matrix multiply. And dense matrix multiply is very well studied and very well tuned, and so start off with a question: can we improve this computation that lots of people have worked on many different machines? So I'll show you a performance plot to start. And this is a strong scaling performance plot. So along the x-axis, I'm increasing the number of processors we're using. And this is on a big Cray supercomputer. Along the y-axis is performance. So up is good. And I've got one curve shown, and this is ScalePack. This is a standard library that people use on machines like this. The other line I'm showing is a dotted line for the machine peak. So this is the best that any classical algorithm could do. And so for this strong scaling plot, if you see a flat line, that means perfect strong scaling. And so this code looks pretty good because it's strong scaling perfectly, but there's a big gap between the performance and the peak performance of what you could hope to get. And so I'll just show you a second curve with a new classical algorithm that does exactly the same computation, but the performance is much better. The difference, the way we get this better performance, is all in reduced communication. Okay, so there's a big speed up to a standard problem by improving the communication properties of the algorithm. But it turns out the classical algorithm for matrix multiply is not the best you can do. You're probably aware of an algorithm by Strawson from a long time ago, and you could try to parallelize Strawson's algorithm. It reduces the computation that you do, and on the left side of the plot for a few nodes, you can actually get better performance by using Strawson's idea. But it turns out that once you scale up to large numbers of processors on this big machine, you start to lose even to the standard scale-back code. But most recently, we've come up with a new algorithm, a new way to parallelize Strawson's idea, which gets much better performance. So comparing the red curve and the blue curve, the computation is the same. It's both using Strawson's idea. But because we're very careful about the communication pattern, we minimize communication with the algorithm. We're able to get much better performance than the old parallel versions of Strawson, and we're able to beat actually the best that any classical algorithm could do. Okay, so the difference between the red and the blue curves, the difference between the green and the black curve is all based on communication. So communication matters. All right, so let me just be a little more specific. I've been talking about parallel machines where communication is sort of clear. It's messages sent across the network between processors. We can also think about communication on a sequential machine. So the standard model for a sequential machine is two memory levels where you have a slow memory, think of main memory DRAM, and fast memory is like a cache, and we're concerned with how much data we move between that link, where all computation happens with data in fast memory. And the distributed memory model is probably more familiar, so communication is happening over a network. Okay, so communication is moving data, and we analyze algorithms to sort of figure out if they're the right ones to tune for our architecture. We can use these high-level models to get at a basic model of their runtime. So the runtime model that we want to think about includes both computation and communication. So the standard way to think about algorithms is just to count how many floating point operations, how many arithmetic operations am I doing. But the more accurate model, especially on today's machines, you really need to take into account the amount of communication, the amount of data movement that's happening. So we can do that with counting the number of flops as units of computation and counting the number of words as units of communication. So if we have some cost per word, some cost per flop, we can get a gross estimate of our running time with these two terms. And so the takeaway here is beta, this is the cost of moving a word, is often much, much bigger than the cost of doing a floating point operation. Okay, so that's been the case for a while, but actually these costs are both improving, but at very different rates, and the gap between beta and gamma is increasing exponentially. Okay, so you probably know that in terms of time, but it's also true in energy. So here's some data to support that. So if we look at the annual improvements in time of flop rates, and this is over the last, say, 15 years, much due to Moore's law and more recently due to multi-core nodes, and compare this improvement of about 60% per year with improvements in bandwidth to DRAM, bandwidth across the network, those are closer to 25% per year. So a big difference in how quickly these are improving. So even if your algorithm isn't dominated by the communication this year, in a few years it likely will. So that's time. But also if we look at energy, in this plot at the bottom, this is actually taken from data for exascale planning. So in this plot, there's several different operations that your machine might do, and on the y-axis is a measure of energy. So the blue curve is sort of where things are now, and the red curve is projected. But what I really want to point out is the comparison between the three operations on the right and these three operations here. So these are all correspond to data movement. So accessing a word from a register is, or from one of the levels of cache, is orders of magnitude cheaper in terms of energy than accessing DRAM, which is this first column, or accessing data across the network. Okay, so if you want to save energy, you want to access data close by and not across your network. Okay, so big differences in time, but we also see big differences in energy, and as that becomes more of a constraint, devising algorithms that minimize communication will help keep down energy costs. Okay, so let me go back to matrix multiplication and sort of look at it at a high level and see if we can explain the performance that we saw on that first plot. Okay, so I'll use n for matrix dimension, p is my number of processors, and m is going to be my metric of how much local memory I have. So I'm thinking about a distributed memory machine where each processor has m words of local memory. So the scale-pack algorithm, what I'll call a 2D algorithm, if we look at the computation, it does n-cube flops divided over all p processors. And the communication scales like n squared over the square root of p. Okay, well, there's a known lower bound for parallel matrix multiply. And if you do these n-cube flops, then the lower bound is given by this expression. So it depends on the matrix dimension, the problem size, and also the size of that local memory. Okay, so you don't have to do the comparison in your head. Basically, the 2D algorithm is suboptimal if you have a lot of extra memory. So if your local memory size is much bigger than n squared over p. N squared over p is like your fair share of the matrices. So if you have a lot of extra memory lying around, that means this 2D algorithm does more communication than necessary. Okay, so as I showed with the green curve on that first plot, a new algorithm, which is called 2.5D matrix multiply, comes up with a communication cost which matches the lower bound. Okay, so it's optimal if you don't have any extra memory. If you have extra memory around, it makes efficient use of it to reduce communication. But the basic takeaway with this optimization is that there's a trade-off to be had. If you can use extra memory efficiently, you can reduce the communication that you do and get better performance. So if the memory is just lying around, you use it. It doesn't hurt anything to use it, and you can get your answer faster. Okay, so that's the sort of high-level theoretical analysis, just to show you a little bit more data to support this. So here's a plot with a fixed number of processors and two different problem sizes. And we're comparing the 2D algorithm, that's like scale back to the 2.5D algorithm. And now the y-axis is time, so down is good. And so the big takeaway is looking at the red parts of these charts. So the red corresponds to communication. Going from the 2D algorithm to the 2.5D algorithm, you cut down the communication by a huge amount, and that cut down your overall runtime. And this problem, so this is an 8,000 by 8,000 matrix multiply across 16,000 nodes. It's very small compared to the size of the machine. Maybe a more realistic matrix size is up in the 100,000 range. But even here, the overall speed up isn't as impressive, but if you look at the red curve, the cut down is about an order of magnitude. Okay, so this performance win is coming just from not changing the computation, changing the algorithm to reduce the communication. Okay, so let me tell you a little bit more about the lower bounds I mentioned for dense matrix multiply. They've been around for a while. So if you do the classical algorithm on a sequential machine, then the lower bound is given by this expression. So this was proved back in 81. And it was later expanded to the distributed memory parallel case, and that's the one I showed you before. And so if you do classical matrix multiply, you have these lower bounds, you have targets for your algorithms. And for these sort of high-level machine models, we've got optimal algorithms, both for sequential and parallel cases. Okay, so that's nice for matrix multiply, and what we've been excited about is that these lower bounds can be extended to a very general set of computations. So let me give you a precise theorem. If a computation smells like three nested loops, then it must communicate by this expression. Okay, by three nested loops, I'm thinking you can write matrix multiply with code that is the three nested loops. And if your computation looks enough like that three nested loops way you can write matrix multiply, then this lower bound will apply. It doesn't matter so matrix multiply smells like three nested loops. It doesn't matter if your matrices are dense or sparse, the lower bound applies, and it applies to our high-level machine models, both sequential and parallel. So that's nice. I haven't really been specific about what smells like three nested loops and why this is exciting. So let me just give you a list of things that smell like three nested loops. It's most of direct linear algebra. So if you know about the basic linear algebra subroutines, they all smell like three nested loops. Algorithms that you use for solving linear systems, so like Cholesky, LU decompositions, things like that, they smell like three nested loops. This lower bound applies. QR decomposition, release squares problems and other things, eigenvalue SVD reductions. So even sequences of algorithms of these types of computations, and even some graph algorithms that are similar enough to linear algebra. Okay, so we have this lower bound, which can be written really simply, just in terms of the number of flops that you do and the amount of memory you have. But the sort of theoretical lower bound is nice, but what really gives it power, what really gives it utility is that it's a target now. For all these computations, we have pretty good algorithms that implement and solve these problems, we can ask now, are they communication optimal? Are they hitting this lower bound, or can we do better? And so that's what we've been working on for the past few years, and we can start to classify all these things. So I'll just give you a little bit of an overview, but we can look at each of these computations, so the BLAS, Cholesky factorization, LU, and QR, and say, are there algorithms out there that achieve them, or should we work on and try to improve? And so I've put some references on the right side, and so you can sort of tell by the years that in some of these cases there are some existing old algorithms which are good in the theoretical sense. And then there are some more recent years showing up that shows some of the improvements we've made more recently. And so this is the sort of story for the sequential case. Parallel case gets a little more complicated, but we can start to do the same analysis. Say, okay, for all these computations, are we optimal yet, or do we need to make improvements? So let me just highlight a couple of these computations. So suppose we have a linear system to solve. We're solving AX equals B, and our matrix A is symmetric, but it's indefinite, so it has negative and positive eigenvalues. If it were definite, then we could run a Cholesky decomposition, and we have efficient algorithms for that. Okay, we're indefinite, which means we need to worry a little bit about numerical stability. And we need to do some symmetric permutations. So what we want to solve this problem is to get a factorization that looks like this. So P is a permutation matrix, so we'll do some symmetric permutations along the way, but we'll get a factorization that looks like L, T, L transpose. So L here is lower triangular, and T, I'll say it's simpler. So once we have this factorization, solving this system AX equals B should be very cheap. Okay, so the standard way of doing this is that T matrix in the middle, that simple guy, it looks like a block diagonal matrix with 1 by 1 and 2 by 2 blocks. So it's LD, L transpose. D is this block diagonal matrix. And that's sort of the standard way of doing things. That's what's in the standard libraries like LAPACK. The problem is it communicates, it's a suboptimal algorithm. It communicates too much. And trying to make an optimal algorithm out of it seemed quite hard. So the pivoting is sort of complicated. We couldn't really see how to make use of that. So we went back to another old algorithm that was devised by Asen, and his middle matrix T is tridiagonal. So it's a little more complicated than this 1 by 1 and 2 by 2 block diagonal matrix. But it's still simple to solve the problem with this. And it turns out that you can take this algorithm, which, so here's a picture of the matrix T is now tridiagonal. It turns out you can make a sort of blocked version of this algorithm, which is communication efficient and solves the problem in an optimal way. Okay, so I won't go into the details of the block version of the algorithm, but the basic idea is we had to go back and find an old algorithm which sort of fell out of use because of the good properties of LDL transpose. But now that this has become more communication bound, we're able to update this old algorithm with communication optimizations and get better performance. So let me just show the performance. This is on a shared memory machine. So now the parallelism is on one node. So this is on 48 cores. And this is a performance plot varying the matrix dimension along the x-axis and performance along the y-axis. So up is good. LAPACK is a standard algorithm for doing this, and the new algorithm, which has much better communication properties, is getting much better performance in practice. Okay, so that's one computation that we ran across where the lower bound applied. The existing algorithm wasn't optimal, and we devised a better optimal algorithm and showed that the performance improvement in practice reflects the theoretical improvement. Okay, so let me give you another quick example, this time coming from a video application. So suppose you have a surveillance video, and what you want to do is subtract the background out of the surveillance video so you can really get at the action going on. And so the robust PCA algorithm was devised to get at this. And so the basic idea is you take your video, and each frame you unfold it into a column of the matrix. So each column, the number of rows in your matrix is the number of pixels in a frame, and the number of columns in your matrix is the number of frames. And what you want is a decomposition, additive decomposition, where L is low rank, it corresponds to the background, and S corresponds to the action. So in this case, people walking around. Okay, so the algorithm is iterative, but basically all the time goes into this thresholded SVD computation. And the matrix, because there are a lot of pixels in each frame and not that many frames, is really tall and skinny. And so if you want to do SVD of a tall and skinny matrix, you always start with a QR decomposition. So basically all the time in this goes into the QR decomposition of a tall, skinny matrix. And that's one of the classic examples of an old algorithm which communicates too much and a new algorithm which really reduces communication by a large amount. And so we implemented this communication avoiding algorithm on the GPU, and comparing the best GPU version of the old algorithm to our new GPU version of the communication avoiding algorithm, we got good speed ups. Okay, so this helps speed up the entire application because all the time was spent in this QR decomposition. So here's sort of a least squares problem, another example of finding a new algorithm and showing implementation improvements in practice. Okay, but to finish out the talk, I want to go back to matrix multiply. And so the question is can we do better than the 2.5D algorithm I mentioned? So I told you it was communication optimal. There was a lower bound. It reached the lower bound. Can we do any better? And what I sort of didn't mention explicitly is that lower bound really assumed that you're doing the classical algorithm for matrix multiply. So if we change that computation, we do something like Strassen, that lower bound doesn't apply anymore. So that means if we do Strassen, can we now beat that lower bound? So let me remind you about Strassen's algorithm. So the basic idea is if you have 2 by 2 matrices and you want to multiply them, Strassen showed that you can do that with 7 multiplies instead of the classical 8. So here's the classical algorithm on the left side. There's 8 multiplies you do, and then you add them together to get your output matrix. Strassen shows you this, taking these weird combinations of entries of A and B. You do 7 multiplies, take a weirder combination of those 7 multiplies, and you get out your output matrix. Okay, but the beauty is you use this idea recursively, and if you solve this recurrence for how many flops you do, you get this n, which is the matrix dimension raised to the power log base 2 of 7. So that's about 2.81. The important thing is 2.81 is less than 3. So that's great. That means you can multiply matrices and fewer floating point operations. But as I've been sort of saying this whole talk, we really care about how much communication you do. So what happens if you implement Strassen's algorithm on a sequential machine and you do it in the straightforward way, you write it recursively? Let's look at the communication costs. So, okay, classical algorithm does n cubed work, and Strassen does n to the log base 2 of 7. If you do the communication analysis, you see this exponent 3 showing up in the classical algorithm, and that exponent becomes log base 2 of 7 for Strassen. So just as we're reducing computation here, asymptotic, I mean in the exponent, we're reducing it for the communication as well. So this is kind of nice. This is a win-win that usually doesn't occur. I mean, usually you have to trade off computation, communication, or something like that. But here you get to reduce both with this idea. Okay, so this guy's excited. I mean, if we want to improve performance, let's use the algorithm that does less computation and communication. But first, I mean, this is just one way. I mean, we just wanted to write this recursively on a sequential machine. Can we do any better than this? I mean, is this communication cost as good as you can do for Strassen? So we worked on that problem and found that, yes, that's as good as you can do on a sequential machine. We can prove a lower bound. It looks really similar to the classical lower bound, but the proof is quite different. But you get this lower bound on a sequential machine. You get a similar lower bound. Just divide everything by p for the parallel machine. And so then in the sequential case, we have a nice story. We have a tight upper and lower bound. So the next question to ask is, well, do we have a tight upper and lower bound in the parallel case? And so we started looking because people have worked on parallelizing Strassen before, and it turns out that all the early attempts to parallelize Strassen were suboptimal. In fact, some of them actually increased the amount of communication that was required. And so because there existed this gap, we had a lower bound, but not an optimal algorithm. We worked hard on coming up with a new algorithm. We called it communication avoiding parallel Strassen. And let me just give you the sort of high-level idea of the algorithm. So Strassen works recursively, and basically the parallel choice to make is that when you generate these recursive subproblems, so 7 in the case of Strassen, you want to decide whether you assign each of the 7 problems to a disjoint set of processors, and so we call that doing a breadth-first search, so you're doing all subproblems at the same time. Or do you assign all the processors to the first subproblem, finish that, and then all the processors second subproblem, finish that? And that's what we refer to as a depth-first step. So those are 2 sort of basic questions of how you could recurse the recursion tree of Strassen, and it turns out you want to take a BFS step whenever possible. It reduces communication to do that. But the trade-off is you pay extra memory. And so that's okay. I mean, if we have extra memory lying around, I don't mind using that to decrease our runtime. So you got to be careful about how you do this at every recursive level. But that's how we got the performance that I showed on the early slide. So this red curve is the CAPS algorithm, and it's beating this blue curve, which does the same computation because it's much more careful about the communication pattern. Okay, so let me just finish with the question that, okay, so we looked at the classical algorithm, we got an optimal communication algorithm, and we said, can we do any better? So let's just do the same thing in the Strawson case. We have an optimal Strawson algorithm, it matches the communication lower bound. Can we do any better? And you guys probably have known that there are many improvements to the exponent of matrix multiply that have happened over the last 30, 40 years. And so here's a plot showing that. So this is years along the x-axis and exponent on the y-axis. So the classical exponent is at 3. Strawson in 1969 showed that it was 2.81. So there's a bunch of improvements here, some of them even recent, even though the slope of this line over 20 years is very shallow. It's still an important improvement. So why don't we start benchmarking these guys? I mean, what are the communication lower bounds for these guys? And so unfortunately, a lot of these aren't practical algorithms. So Strawson is practical. I mean, I showed you we're getting better performance in practice. But not all these guys are practical for various reasons. Maybe I won't go into them now. But not all of them are impractical. Not all of them are only theoretical. And maybe we can't get the exponent to 2.3 right now and remain practical. But we can have modest improvements in the exponent and still remain practical. And furthermore, Strawson really prefers to have square matrix multiply. So it wants to divide things evenly. And there are many algorithms that work better for rectangular matrices. So if we can make use of those, then we can actually do better than Strawson. So these are some very recent results. We're working on this right now. But here's a performance plot. This is a sequential machine. And the black curve is Intel's math kernel library, which is a very efficient implementation of the classical algorithm. The red curve is Strawson. And so even for small matrix dimensions, so this is in the hundreds, Strawson can show a performance improvement. But there are these other algorithms which are sort of encoded with numbers like 3 and 4, which are already beating Strawson for these shapes. So it's possible to beat Strawson. These guys actually have better communication characteristics in theory, and so we've got some initial results to say that, yeah, we can make them practical, and our parallel implementations of these algorithms are underway. Okay, with that, I'll thank many collaborators on all this work. We also had finished a recent very long paper for Acts Numerica, so if you can wade through 150 pages, there's lots more details if you're interested. And with that, I'll thank you very much. Sure, I think we need to use a microphone. I think she's coming there.
Very nice, Gene. I have a question. Your first matrix was of order about 10 to the 5th.
Right.
I always tell my students in scientific computing that matrix multiplication for large, dense matrices doesn't occur. It's only a theoretical result. Do you know any applications where you get matrices, say, even of size 10 to the 4th? Not even 10 to the 5th.
Sure.
Are there such applications?
So there are. So there's some computational chemistry applications that have motivated some of this work. You can still make the argument. I mean, so people are multiplying. They're in the form of tensors, but they're doing matrix multiplication of this size. You could argue that there's some structure in those matrices. So they're dense, but there might be other ways to avoid doing these big dense matmals. But that's what they're doing right now, and so that's one application where we might be able to help by coming up with algorithms like Strawson.
But if it's 10 to the 5th, then you need 10 to the 10th elements. Where do you get the 10 to the 10th elements?
Inside the application?
Well, if you're multiplying matrices of order 10 to the 5th, that means there are 10 to the 10th elements in the matrix. Where do you get 10 to the 10th elements?
So I mean, I think they correspond to interactions between orbitals of these small chemical systems.
And where do those numbers come from?
Some sort of integral relationship. I don't know the details of how they compute them.
Okay. Because I find that hard to believe that you're dealing with matrices of size 10 to the 10th for real applications. But that's my question.
Okay,
We can
okay.
follow up afterwards.
Okay, sure, sure.
Hi. Does the strengthened algorithm have longer critical path than the classic matrix multiplication algorithm? Is this a problem for the scalability of these algorithms when they're extended to many machines? Thank you.
Sure. So the critical path is not longer. So all these subproblems are completely independent. So that's nice. There are some additions to be done, and some of the optimizations of Strasson's algorithm involve a few more dependencies. So those can be a little bit of a hindrance. But if you only do a few steps of Strassen before switching to the classical algorithm, it usually doesn't get in the way.
What is the state of the art on irregular algorithms problems?
So I think I'd steal Andrew's thunder if I answer that question. So I think Andrew will spend a lot of time on irregular applications.
One last question.
So once you've divided up the problem in recursive algorithms, you need to have a base case of what's good granularity for the machine. How does that granularity interact with the recursion?
Right, so are you thinking more on one node or in these big distributed systems?
So if you have either multi-core or where you have local caches or a distributed system where you have memory and local caches, how do you decide the granularity at which you stop the dividing it up and doing the recursion? That's the first question. And then does that granularity affect the scalability and the parallelism at the second granularity? Because these systems are all big and complicated, right?
Right. So a lot of that depends on the performance of the classical code that we call. So if we have an Intel machine and we're using MKL at the base case, we decide that empirically based on the performance of the different base case sizes.
And then does that choice? And then my second question is: does that choice affect the different ways to do the partitioning? Does it change the shape of the problem at the higher level, or do you because they're rectangular, not square? Is it influencing how you divide up the work?
Right. So yes, that will happen. So for the big distributed systems, we haven't tried these rectangular algorithms yet. So I think that will complicate things. For Strassen, it doesn't really matter. They're sort of separate.
Everything's square.
Yeah.
Thank you. This is really interesting work.
Thank you.
Thanks.
So the next speaker is going to be Andrew Lenhardt from UT Austin. So he is a research associate in Keshav Pingali's group there. And he's the primary implementer of the Galois system, which is what he's going to be talking about right now. He graduated from UIUC, working with Professor Vikram Madhve. Andrew?
Oh, sorry. There's preview slides there. Okay. So I'm going to talk about something entirely different almost from what we just saw, which was classic regular algorithms. So going to this question about what do irregular algorithms look like right now. So I will spend some time on that. So this is kind of the required slide for all these kinds of talks, which is parallelism is everywhere. And I'm going to be very fuzzy about what that means right now. But basically what I mean is it's exposed to the user, right? In the high end, we've seen this for many, many decades, going back to the 60s. But now we're at the point where someone programming a phone needs to be aware of parallelism to get good performance, right? It's now the second most important thing to get your performance on these machines over using your cache well. Right, so that leads to the question, how has parallel programming tools evolved over the years? And there's been a lot of work, and there's a very mature theory involving, in the compiler realm, involving data dependencies and now various static analyses for things like matrix multiply that do very well. They're at the point that any good compiler you get is going to implement a reasonable subset of them. And these are focused very much on very classic HPC algorithms, which look like triply nested loops or doubly nested loops. Now, once you start saying, I need all my algorithms to be parallel, a lot of algorithms don't look like that, right? They don't use matrices or vectors. They use sets, hash tables, trees. And these static methods really start falling down once you're exposed to these very more complex irregular data sets where you can't predict what's going to happen, often until you've already read your data. All right, so I'm going to talk today about the Galois project, which is a project we've had going on for 5 or 6 years now, which is looking at parallelism not from kind of a loop-centric computation standpoint, but from a data-centric standpoint. I'm going to focus on parallelism, but you can use the same kind of analyses to reason about locality, and we do. And I'll talk briefly about our implementations on multi-core systems. So I'll talk about up to large-scale NUMA systems, GPUs, various other accelerators. We have work going on in hybrid and distributed memory, so I won't touch on those very much, but you can ask about them if you want. And so let's consider kind of the classic approach we have right now in compilers, which is focused on these HPC examples. So here, there's a very simple, for clarity, finite difference computation, right? So what are you doing? You have 2 arrays, and they represent 2 timestamps, and you're computing a new timestamp from an old timestamp, and you're looking at the value of an array element and its neighbors, and maybe you're computing how heat is transferring between that discretization of your surface, and you're computing a new value. The key thing is these 2 arrays are completely distinct. The compiler can prove you're writing to unique locations in the new array. The other array is read-only. That's easy for the compiler to prove as long as it can prove the 2 arrays are separate, but that's a whole different compiler realm. And once it does that, it basically can do arbitrary restructuring of this loop, introducing parallelism, optimizing cache locality, using the mature theory. But let's consider a slightly less regular algorithm, which is Delaunay mesh refinement. This is also actually an HPC usable algorithm. People use this, and what you do is you take a triangular mesh, and in this mesh, some of the triangles are going to be misshapen. They're going to be very narrow, so their aspect ratio doesn't lend themselves to numeric stability. So what you want to do is you want to take those triangles and replace them with better shaped triangles. So what we're going to do is we're going to read a mesh, and we're going to look at all the triangles in the mesh, put the bad ones, these misshapen ones, in the work list, and we're going to go over the work list, pulling a triangle out, finding some data-dependent area around it, replacing those triangles with new triangles. Some of those new triangles may also be misshapen, and in which case we're going to put the misshapen ones back in the work list, and we're going to keep going until we run out of bad triangles. And at least in 2D, under certain constraints, this is guaranteed to eventually happen. Now, if we think about the classic parallelism, we would look at this loop and say, okay, what data dependencies exist? Well, every iteration reads and writes the work list, which already means it's a serial loop and there's no parallelism. But even if we ignore the work list, you can't, from this loop, say what triangles touch other triangles, what iterations are independent from other iterations. There's no data for that until you've actually loaded your graph, right? So the compiler can basically do nothing here because it doesn't know what the mesh is going to look like. And the problem here is this is a computation-centric view of parallelism. But if we actually look at what's going on, so on the top left, I've marked the bad triangles in a simple mesh in red. They're triangles that you need to look at to be able to replace those red triangles. And just intuitively looking at this, all of those red triangles should be able to be replaced in parallel because the data each computation needs doesn't overlap. It's independent. But you're not going to discover this actually looking at the body of the code. So we're going to look at a data-centric view of parallelism. Oops, wrong direction. All right, so here's our data-centric view of parallelism. It has several components. The first is what we call an active element. If we're going to think about parallelism from a data perspective, the question is, where do you need to do computation? And where you need to do computation, I've marked in red on this graph. So in DMR, where you need to do computation is a bad triangle. In SSSP, where you need to do computation is a node to which you've changed the distance label on. Right? So it's an algorithmic dependent property, but It's just a general notion of where should we actually do computation. The next question is, what computation should you do? This, the programmer has to give, right? So in DMR, the computation you have to do is to search the local area of a graph, collect a set of triangles, replace them, etc. This is what we call the operator. It's the code the user wants to actually apply to the graph. Now, one thing we don't know, because in this irregular realm, is what data you're going to touch, right? So in DMR, you touch a input value data specific region of the graph. It's not just your immediate neighbor triangles. It could be hundreds of triangles. It usually isn't, but it could be. And we call this the neighborhood of an activity, right? It's the data you need to perform your computation. There are many kinds of algorithms, but they fall generally into two categories. So DMR is an example of an unordered algorithm. You can replace triangles in any order you want. It doesn't matter how you process them, you will get correct triangulations out of the algorithm. Single source shortest path, there are algorithms that have this property too. They're fixed point algorithms, right? Some orders might be more efficient, right? Dijkstra's is a particularly efficient order, but other orders will get you the correct answer eventually, right? So for correctness, we don't need to care about the order. For performance, we might. But then there's other algorithms, say you're doing like a billiards ball simulation or discrete event simulation, same thing. The order you process things in is critical to the correctness of your algorithm. So these are the two classes of algorithms. I'm going to talk about unordered for the rest of the talk. Ordered's another complexity. And once we have this view of our computation, this leads to a notion of what we call amorphous data parallelism, right? As long as we respect the ordering constraints on the work that needs to be done, if the neighborhoods don't overlap, we can execute things in parallel. Right, so there is one neighborhood I've highlighted for one particular activity. This one here overlaps that guy, so they can't be done in parallel, but maybe these other two are perfectly parallel, right? So we can run three things at once. But we don't know that we can run those three things at once until we actually load the graph and look at it. So one thing you have to consider is, where do you introduce parallelism in your code, right? So the classic methods are trying to do static parallelism. You look at the code, maybe parameterized on the size of your matrix, you parallelize your loops. And you can do that because you have all the information you need at compile time. But for something like a graph, you actually need to know what the graph looks like. So think about something like BFS. If I have a very branchy graph, I have lots of parallelism, right? Because I can do lots of paths down the graph in parallel. If I have a straight line, there's no parallelism at all. So I may have to actually load my data first and look at it to figure out what parallelism exists. BFS or SSSP are simple because I can look at the code and tell you, if you give me a node, you're just going to touch your immediate neighbors in the graph. Something like DMR doesn't have that property. You don't know what data you're going to touch until you start inspecting the various coordinates of the triangles with respect to the triangle you started with. So there you actually have to discover the data you need to use for each task. And you could, for example, discover all these neighborhoods, compute an interference graph, execute a parallel independent subset of that. There's also various approaches with speculation, which I won't talk about. So we have a particular implementation of this view of parallelism we call the Galois System. And this is really trying to get a very simple to program system for your typical programmer, right? Our goal is so that your normal programmer can write correct parallel code without being exposed to things like synchronization. We do this in a very similar way to languages like SQL. You have a simple front end, and then expert programmers deal with all the complexity and translating to actual machines. So what is Galois? Concretely, it's a library of concurrent data structures, and it's a runtime system that optimistically discovers parallelism, deals with conflicts between tasks when they're running, discovers these, and executes code. To the normal programmer, they write in sequential C++. So we actually provide a serializable view of their loop, and they're not exposed they're not exposed to any synchronization. And we do this without transactions, but that's a whole nother talk. Right, so your typical programmer can just stylize a for loop, use our data structures, and they'll get a correct parallel execution. All right, so what does a Galois program actually look like? This is kind of about the simplest you can get. Galois is a C++ framework. We declare a graph. In this case, it's a compressed sparse row representation. It has data of type struct data on the node. There's no data on the edges. It's a directed graph. We write our operator as a C++ functor. Now, if I were redoing this slide, it would be a lambda because they're much nicer to write. But this is this is just going to go over, take a node in the graph. It's going to get the data on the node. It's going to take that particular field, add 1, right? It's just a toy example. But there's no restriction on what data you can access. As long as you can reach it through the data structure, if you want to touch every node in the graph, feel free. If you want to touch your neighbors, that's fine. If you want to do some random walk, great. And then we just have a stylized loop here that takes some things to work on and executes them. We use a dynamic task model, so operators are free to add more work to the work list at runtime. There's a whole domain-specific language for scheduling, which I'm not going to talk about. So there's a bit more to a good Galois program than this, but this is a good minimum example. Now, given that we're doing all of this stuff for the programmer, can we actually get good scaling and performance? And the answer is yes. So here is an SGI Ultraviolet. This is a large NUMA machine. Each blade has 2 boards. Each board has 2 packages of 8 cores, each connected by internal network running through SGI's directory controllers. Between blades, you have another torus of connecting those directory controllers, right? So this is a classic NUMA machine. And here we see scaling for some graph analytics and more HPC-like algorithms of 50 to 80% at 512 cores. And so this is non-trivial scaling. Now you might say, self-relative scaling is easy if you start with a bad baseline. So hopefully, if you want to read the table, you can. Suffice to say, the baselines we're starting with are competitive or better than handwritten implementations of these particular algorithms. Right? So we're starting with. So we're starting with decent baselines. I said we've had a lot of work on implementing these on GPUs. The execution strategy is fairly different from what you need for a CPU, but if you do it right, the latency masking on a GPU lets you get very good implementations, assuming your problem fits. If your problem doesn't fit, we've been working on that and some hybrid execution to swap in and out parts of the graph. I won't show any results there yet. We have compared to other graph analytics frameworks. This is an area where there's lots of work right now in the more narrow area of graph analytics. So on the left, we're comparing to a couple of graph analytics frameworks, Ligra and Paragraph. Paragraph is the distributed version of GraphLab. And the key takeaway here is that these are frameworks that are restricted programming models. You can write to a node, and you can read your neighbors. And that prevents you actually from writing the most efficient algorithms we know for some of these problems. Like for connected components, you can't do path compression because that's not expressible in the DSL. So having a more general programming language actually lets you express better algorithms to solve some of these problems than some of these other frameworks. You might ask, what if we fix the algorithm? How do you do? On the right, basically what we've done is we've taken the benchmarks provided by these other systems, wrote an API shim so that we could use our runtime with their API. And there you see that for parallel graphs, which is the top row, they do pretty well. But once you start getting high diameter graphs like road networks or planar graphs, the performance concerns you have to take care of change considerably, right? So if you're over-optimizing for parallel graphs, you might do very poorly on these other classes of graphs. Exactly why this is going on, we could talk about after if you would like. Now, that was our comparison. You don't have to believe us. There was an Intel study recently published. The left blue bar is where Intel threw some engineers over the course of 6 months or so at these problems and wrote hand-tuned implementations. And the far right bar is what we were shipping written by a couple of graduate students, right? So more or less there's often a very small performance hit from having all these automated things happening for you in the runtime, but it's very, very competitive with handwritten code. And often, much better than the competing frameworks right now. Hopefully they will get better. But now that just says that you can take our code and the benchmarks we've written and get good results. Unbeknownst to us, some people at Berkeley went and downloaded our framework, which you can do too, implemented their FPGA place and route tools, and without any hints or performance hints from us, they didn't talk to us. They also could get very good scaling. Right? So this is a very different class of problems, and it's quite applicable. So in conclusion, think about parallelism from a data-centric view. Don't think about having to preserve loop dependencies where that's just a construct of how you solve the problem, rather than what's something inherent in what your algorithm actually needs to do. So we think about parallelism data-centrically. We have a particular formulation we like. We have what we think is very good implementation that has scaled to very, very large machines. On top of this implementation, we've been doing various work in domain-specific languages. So can you express graph algorithms as a simple rewrite system? There is a working but not yet optimal or released distributed memory system where you can take the same source, C++ source, recompile it, and get a distributed memory application out of it. Essentially because we already mediate, the data structures in Galois already mediate access to data. So if there are distributed data structures, the code that uses them doesn't have to change. We have a lot of work, as I said, on hybrid execution, CPU, GPU, Intel fees, distributed heterogeneous. That's all work in progress. So you can feel free to go download the code, try it yourself. We have some benchmarks, both CPU and GPU irregular benchmarks. If you are interested in doing work with irregular algorithms, you need a non-trivial benchmark set. By all means, use some of our benchmarks and read some papers. Thank you. Any questions?
Thanks. Great talk. So you said that at the beginning that you were talking about parallelism, but you could use this for locality as well.
Yes.
So I'm very interested in locality.
Yep.
And the one difficulty I see is that the locality basically depends on the data structures, which often you don't know until you read in. But when you read in, you often have put them in memory, which may be what you didn't want to do or want to do a different way. So
Yeah.
I'm curious how you handle locality.
Yes. So you're not going to get good scaling on a NUMA machine without dealing with locality. We don't alleviate the need to express a partitioning if your data is partitionable. But if you have a partitioning of your data, we can lay it out in the particular machine's memory correctly, and we can do scheduling of tasks based at least on where they start in memory. So we can preserve locality that way. All the data structures are NUMA aware, so they are aware of how the memory banks are laid out between the cores, and they, you're not going to have nodes and its edges in different memory banks, for example, and we're going to schedule tasks from the right cores. Beyond that, there's a question where something like DMR, where you're recursively producing tasks, there's temporal locality you can exploit, and that's a property of what order you do tasks in. So this is actually one of the reasons why we have a language for expressing scheduling policies. So you would tell us, I want something that looks kind of like a local LIFO, right? The tasks I just generated should be done first because I know that if I do them first, I will get higher locality, which is the exact schedule that serial code, handwritten serial code uses for that problem. So we just want to make sure that if there's a particular schedule for your algorithm that's good, because it captures locality or because it captures algorithmic improvements, reductions in algorithmic complexity, that you can express that to the runtime, and that we have good implementations of that.
Have you developed any understanding which resembles what the prior talk gave about the relationship between the communication need, especially when you have a very irregular layout where things can really be messed up relative to the best we can do, and whether sometimes you run into situations where you can do very little? Somehow I was looking for some understanding at the level of the prior talk, and I didn't see any theory here or any analytical issue.
Yeah, so communication optimality is really going to depend on your particular application. Right, the runtime doesn't know these things. Now, the runtime itself is very, very communication aware, so all the internal structures like the work lists are aware of the communication costs between themselves and other threads, and we do a lot of topology-aware optimizations there. But we can't tell you for a particular algorithm what the minimum communication cost is, right? Because we're not, that's not the layer of the stack we're writing at. So if you know a particularly good way of executing your algorithm for communication, we'd hope that you'd be able to express that using a combination of data layout and scheduling. But we can't automate that because that's a per application thing.
So you view it as something which is beyond scope for your work?
It's something where if you know what it is for your problem, you should be able to express it in this language.
Okay.
And internally, where we do have things like barriers or work lists, we've optimized that as best we can according to communication minimization. Right?
Okay. So my other question is, what is the difference between what you call amorphous parallelism and the work depth outlook that was developed in the parallel algorithmic communities in the 80s?
Sorry, and the what?
There is a term called work depth parallelism, which you can find in any textbook on parallel algorithms. And the question is there any difference between that and the amorphous parallelism that you described?
I'd have to get back to you on that.
Okay, let's thank the speaker again. So I'm your third speaker. So I'm Madan Muswati from Microsoft Research. I work in RISE, which is Research in Software Engineering. And recently I've been interested in parallel algorithms, especially trying to parallelize algorithms that look sequential. So this is a slide that we have seen in Andrew's talk. Like, hardware is parallel, so there's parallelism all around, starting all the way from FPGAs to your phones to the new amount of parallelism we have in a data center. But there's a lot of algorithms which are sequential, right? Think of it like the 99% of the algorithms which are not able to make use of all the parallelism that we have. And we would like to somehow, try to see if we can make use of all the hardware parallelism in order to make these algorithms go fast. So here is my motivating problem. I want to grep terabytes of data in seconds. So why is this problem interesting? I'm going to argue that this is a quintessential big data problem, where you have lots and lots of data in arcane, unstructured formats, and you would like to be able to parse them and look for patterns, look for useful patterns. And in many cases, you don't even know what patterns you're looking for. So you actually want an interactive system where you can try your different things, and the system will get back to you in seconds, so that you can refine, look at the answers, refine, and then try again. And we like to support something like a very rich querying language like what we are used to with grep, right? Like a regular expression language where you can ask different kinds of queries. And the basic problem is that if you have terabytes of data and you're trying to read it sequentially from the disk, it can take hours, right? And so the only way in which you can make the system interactive is to use I/O parallelism. Take this data, distribute it along on like numerous disks, like thousands or 10,000s of disks, and do your computation in parallel. So in that sense, if you want interactivity, you're forced to use parallelism. But the problem is that all the implementations of grep that I'm familiar with, right, they are sequential. They are based on like building a finite-state machine that processes the input 1 byte at a time, right? And so there's no way you can do a grep within seconds. And this is has been one of the motivating problems. And in this talk, I'll try to show how we can go about trying to parallelize these sequential computation. So first of all, I'm going to take a few steps back and look at why some algorithms are difficult to parallelize. It's because of these sequential dependencies. Let's say you are doing some computation F, which is producing an output which G requires in order to operate to produce an output for H, and so on, right? So you have this computation where there's a sequential dependency. And in order to do this computation in parallel, you need some way to break these dependencies. And we know of many instances where you can parallelize despite these dependencies. A simple example is, let's say, if every block here is adding some numbers, right? Since addition is associative, you could break up the dependencies, do things out of order, and then put them all together, right? Now, what I'm going to tell you is something very surprising, which is that you can find an associative operation in any computation, right? For example, if you look at this, you can think of this as a function composition, right? You're applying the function f, then you're applying g, then you're applying h, and then I. And function composition is associative, right? So at least in theory, there's a way to do things out of order and parallelize them. So let me explain this by focusing on just one sequential dependency. Let's say we have f producing an output that g requires, and we want to break that dependency, right? So what I'm going to do is that I want to be able to run g in parallel with f, but I don't know what input to run g with, because that input is generated by f, right? So instead, what I'm going to do is I'm going to assume that g is going to take some symbolic value x, right? I don't know what it is, but I'm going to treat it as a symbolic value and then do this computation symbolically, right? And so what I would get is hopefully a simplified expression that tells you what the output of g would be given a value of x, right? Now, once I do this, and I'm going to do this in parallel while f is computing the value, right? Once I know f's output, I can essentially plug it into this formula to get the output of the entire computation, right? So this is another way of saying that, I can take function composition and then it's associative and do things out of order, right? And this is not a new thing. People have known this for a very long time, since the 70s and 80s. And in fact, if you look at the way your adder works in your hardware, the carry look ahead adder, you can think of that algorithm to do addition efficiently as an instance of applying this idea. Okay? But at least for me, right, I used to, whenever I would see these dependencies, there would be a mental block which would say, oh, that means I cannot parallelize it. By looking at it this way, it sort of relieves this mental block. And now so essentially, in order to parallelize some computation, I have to solve two problems. So first problem is, can I actually do this symbolic computation efficiently, right? Because I'm actually, g is running symbolically in parallel while F is doing its regular computation. So the symbolic computation better be really fast. And the second thing is there simplification achievable so that evaluating, substituting B in that formula is actually more efficient than running G in the first place, right? So these are the two problems that I would like to solve. And what we have done is looked at several instances of algorithms where we have taken this idea, stared at it, and came up with algorithms that could do both of them efficiently. So, so first we looked at finite state machines. So this was motivated by the grep problem, where we actually have a regular expression engine that is actually data parallel. So we can make use of any kinds of parallelism that you can throw at us. Including instruction level parallelism. So that's why we are actually 3 times faster than the sequential implementation on a single core, and we get linear speedups beyond that. And we've also applied to classes of dynamic programming optimization problems like Viterbi. And I can safely say that we actually have the fastest software Viterbi decoder. And the reason why I can confidently say that is that we actually took previously the world's fastest software Viterbi decoder and used it as a black box to actually add additional parallelism and get linear speed up beyond that implementation. So if you have another implementation which is faster, then we can actually parallelize that as well. So we actually linear based on any sequential implementation that you could give us. And we can actually, our software decoder can beat a commercial FPGA implementation in terms of throughput, where our implementation is running on CPUs. So I'll dig deeper into each of these two problems, and first focus on the finite state machines. And finite state machines are it's a fundamental aspect of computer science. There are lots of applications. I already mentioned grep. Then the other thing is tokenization. Let's say you want to parse HTML web pages. Another interesting application is Huffman decoding. So the way Huffman decoding works is that you have a decoding table that you're looking up on every byte to find out how to decode your input. And since you have a dictionary is finite state, you can actually encode that computation as a finite state machine, and you can use our algorithm to parallelize it. So I'm going to start with a very simple example of a finite state machine. So this is a state machine with 4 states that accepts C-style commits, right? This is just for demonstration purposes. And what happens is that the way you implement a finite state machine is that you actually have a lookup table, something like this, right? And you start from the initial state. And what you do is that for each input, you look up the table to find out what the new state is, right? The new state depends on your current state and the next input character that you read. And this is, I mean, if you look at this example, there's hardly any place where we can exploit parallelism, right? Because of this dependency between this state in the previous iteration to compute the state in the current iteration. And even the loop is not doing a lot of computation. You're just doing a series of memory lookups. So there's hardly any ILP to actually use in this example. Okay. And so we're going to use this technique to break the dependency here. Let's say how we can do this. Okay. So let's say I have a sequence of input, and I would like to parallelize it on 2 processors, P0 and P1. Okay. Now, for P0, it's what I can do is I can actually start from the initial state and process 1 byte at a time and do your regular computation. But the question is what I'm going to do for P1, right? So remember the example I said before, right? So we're going to start with the symbolic state. The nice thing with finite states is that You can do this for all. You can do this for all execution by explicitly enumerating all possible finite states of this finite state machine. Right? So in our case, we have there are only 4 states. So what we can do is like essentially run the finite state machine for each of the possible initial states. Right? So there are 4 ways, and so we will run it for all possible 4 states. Now, one thing that you might say is that, what do you want to do with all 4? Why can't we just guess? And maybe we'll just speculate on, and by staring at the finite state machine and say, okay, maybe it's most likely to be A, right? The starting state is most likely to be A, and so let me just speculate for just that state. The problem with that is that you might be wrong, and if you're wrong, you have to throw away your computation and then redo from the correct state. But we can avoid all that by actually doing this for all execution, because there's no way in which there's no misspeculation, so you don't have to go back in time. Now, the one problem with doing that is that you are doing 4 times more computation than the sequential version, right? So and so whenever we are parallelizing, these constants actually make a big difference. So imagine you have a state machine with hundreds of states, right? And if your parallel version is 100 times slower than the sequential version, then you will only get a speed up of 2 on 101 cores, which might not be very practical. So we have to somehow come up with a way to optimize these constants away from your algorithm. And that's where our key contribution is in trying to figure out ways to hide these constants in this algorithm. Okay? And one thing that I've done here is actually colored the states so that some redundancy is actually visible in this computation. So if you look at these 2 states, C and D, on reading a star, they both of them happen to go to the same state. Okay? So what this means is that the rest of the computation starting from here and here are going to be exactly the same. And so you don't have to redundantly repeat them, right? So what you can do is that you could sort of remove one set of computation, saying that both C and D go to D, and so there's no need to repeat the 4th computation. You can also do the same thing in the 2nd step as well. So as you can see, you started with doing 4 times more computation as a sequential version, but you dynamically looked at how these states converged, and you use that idea to actually reduce the amount of computation that you're doing. Okay? And we have found that, so essentially, like, the cost of doing this enumeration is proportional to the number of unique states, not the number of states in your finite state machine. And what we have found is that for many finite state machines that you get in practice, they have enough structure that there's a lot of convergence in these finite state machines. Okay? And here's a graph that demonstrates this. So what we did is that we actually looked at around 2,700 regular expressions from a benchmark of regular expressions called SNART. And for each of the regular expression, we converted into a finite state machine, and we found out that input that actually is a worst case input in the sense that it causes the least amount of convergence. Okay, this is the worst thing an adversary can do to our algorithm. And what this graph plots is, on the x-axis we have the input length as generated by this adversary, and on the y-axis the proportions of finite state machines that converge to less than 16 states is the black line, less than equal to 8 states is the red line, and less than or equal to 4 states is the green line. Right? So the high level thing is that as you increase the input, many finite state machines actually converge, right? So some of these state machines have as high as like thousands of states, but they converge to very small number very quickly, okay? And so just to highlight some two points here, right? 90% of these finite state machines converge to less than or equal to 16 states just after 10 steps, right? And but interestingly, only 65% of them converge to less than or equal to 4 states, right? So even after 5,000 steps. So just the high level point being that there is a lot of convergence, but not convergence to 1, right? So we need to converge to 1 in order to be competitive with the sequential version, right? In order to get near linear speedups. But we can reduce the constants from very large numbers to somewhere between 16 and 4. Okay, which is something that's reasonable. And so what we did was we actually used vector instructions to hide this additional constant so that we are competitive with the sequential version. And so this graph shows our performance of the parallel algorithm when we are hiding these additional constants in SIMD. And I'm actually hiding a lot of details between the two slides here because we worked a lot on trying to get the SIMD version to perform really well. So again, what this graph shows is for randomly selected, I think, 250 regular expressions. And on the y-axis, we have the speed up, the sequential speed up over the baseline, the speed up over the sequential baseline. And as you can see, for many regular expressions, we are actually 3 times faster than the sequential version. This is because since we are parallel, we can actually process multiple bytes at the same time. So we are able to make use of instruction level parallelism, and that's why we are much faster than the sequential version. And but there are some finite state machines for which we are slower, and so we are like up to like 4 times slower than the sequential version. But we can hide that by actually scaling to multiple cores. And here you see the speed up of our technique on Bing tokenization, which is again a finite state machine, and we get near linear speed ups on multi-cores. Okay. So now I'm going to quickly, I just have 5 minutes, but I'm going to quickly go over how we apply this technique to dynamic programming. So there are many optimization problems which can be phrased as trying to solve in terms of dynamic programming. And so the best way to think about it is that you have a table and you want to fill up these tables with values, and there's a formula, there's a recurrence equation that will tell you how to fill up a particular entry if you know the values for a set of previous entries. Okay? There are many optimization problems that can be phrased this way. 2 important things is like Viterbi and diff, which is trying to find the longest common subsequence of 2 files. Okay? And again, if you look at these recurrence equations, usually you can group these cells into stages. And as I have done, so in the Viterbi algorithm, each column is a stage. And in diff, each anti-diagonal is a stage. The way I've grouped this is that in order to compute the values in a stage, you only need values in the previous stage. And you can actually, there is parallelism within a stage where I can compute all the values in a stage in parallel. But what we are interested in doing is that, if you look at the sequential computation where I'm computing one stage after the other, I somehow want to break the dependencies across stages because we want to get more coarse-grained parallelism by which you can split the table in multiple cores or multiple machines and compute them separately despite dependencies. Okay? And our algorithm works when the recurrence is of a particular form. So I will not go into the details, but the basic idea is that with our restrictions, we can actually phrase the optimization problem as finding a shortest path in some graph. For example, in this graph, each of the cells is going to be a node, and there are going to be edges between the different cells where there's a weight on each of these edges, and you're interested in finding the shortest path from this node to this node here. Okay, and so let's say I want to do this computation in parallel, and I want to split the table at this point. Now, the problem here is that I don't know where the shortest path is going to intersect this boundary here. Right? So in this case, it happens to go through this first node, but it could be on any one of these nodes. Right? And so we actually, again, use our idea of like the for all computation, where what we do is that split the table into two parts, compute all the shortest paths from the source to all the nodes in the boundary, and the shortest paths from all the boundary nodes to the destination. And if I can do this computation in parallel, then I can actually put them together to find out the shortest path between the source and the destination. And essentially what I have done, so just extending this, if you want to do it on, break the table into multiple pieces, I essentially have to solve the all pair shortest path problem from the left side boundary to the right side boundary. And that, again, the overhead is proportional to the size of the stage, right? Because I've converted, the sequential version is doing the shortest path problem, and the parallel version is doing the all pair shortest path problem. And we actually have some techniques to actually reduce the computation of the all pair shortest paths. And the basic intuition is that so let's say you look at a road network, and you're trying to find the shortest paths from all pairs on the West Coast to all nodes in the East Coast. And the intuition is that the road networks have some structure. There are going to be these highways through which the shortest paths have to go. And there are only a few ways to go across the Cascades and the Rockies, for instance. And there are only a few bridges across the Mississippi, right? So all this structure is going to mean that many of the shortest paths will actually converge to cross these bottleneck points, right? So this is the same intuition that we are actually seen in practice as well. So this is actually doing the shortest paths in a particular instance of finding the least common subsequence of two DNA sequences. And as you can see, if you want to find the shortest paths from all points here to all points here, they seem to be going through this particular instance here. And so we actually use this structure to do the all pairs shortest paths as efficiently as the single source shortest path. And based on this technique, we actually get really good speed up. So this is the speed up over a software Viterbi decoder on multiple cores. And as you can see, we are getting very close to a linear speed up. So with that, I'm going to conclude. So I demonstrated how we can break dependencies in classical algorithms in order to get parallelism. And the basic idea was to use some kind of dynamic convergence properties. In the finite states, we use the fact that many states converge to the same state on reading inputs. And for the dynamic programming, we use the insight, the fact that this all pair shortest paths actually go through these small bottleneck points. And the interesting question is, can we actually apply these ideas to other algorithms? That might be interesting. For example, we've been looking at parsing. And can we actually do context-free grammars parsing in parallel? Can we apply these ideas to graph algorithms and so on? And one thing that we are also very interested in is see if we can automatically parallelize by breaking these dependencies. So currently, we are doing it manually. And we hope in the future we'll be able to come up with a sophisticated compiler technique to generate new parallel algorithms. So with that, I conclude, and I'll be happy to take some questions.
So my objection to what you're doing is that you seem to be desperately trying to convert every algorithm into a divide and conquer?
Yes. Why is that a bad thing?
Problems are not inherently. There is no inherent general purpose structure which will always allow you to do that. Okay, it's in the case of some specific problems like yours, maybe it's possible to do.
Yes. So in the sense, let me. If I meant to say that, I would like to.
Your dynamic programming problem is also next. What you're going to do is matrix multiplication, right? I mean.
No, matrix multiplication.
It's on semi-rings,
right? So I'm interested in improving the class of algorithms that we can parallelize currently. And so I'm not trying to take every computation and try to parallelize them. But my hope will be that there is useful algorithms that we need this additional parallelism for, and we can come up with algorithms for those computations. And so as I mentioned about grep, right, it'll be really nice if we can apply, if we have a grep-like tool that can parse and find patterns in petabytes of data in seconds. And I think it's an important problem in practice. We don't have a parallel algorithm, and it'll be useful. That's why this area is interesting, right? But you're right. I don't want to make all algorithms parallel, right? I mean, I wish I could, but there has to be. I mean, if there's a good application for it, then the problem is interesting. Thank you.